Good morning. So I am Tathagata Roy. I am currently a first-year master's student at WU Amsterdam, and I'll be talking about Coccinelle for Rust, which is a tool which I've been developing with Dr. Julia LAWALL. So before I get into what it is, I'd like to speak about why we need it. So huge code bases such as the Linux kernel have a lot of code. Linux kernel, for example, has 23 million lines of code, and more than half of which is just drivers. So one of the main challenges is collateral evolution, which is when a main part of the C API changes, the Linux drivers need to update automatically, and if more than half of the half of the kernel code is drivers, it would be hard to manually change everything, especially in a timely manner. So Coccinelle for C was made to help with automating the process. It provides semantic patches which give a form of generalized view of the diffs we get, and it applies them to each and every file in the repository. So there's a small example, and Coccinelle for Rust is the version of Coccinelle for C, but for Rust, as the name implies. So this is an example commit in the Rust C repository. Here, as the commit says, it changes, it just changes calls of type of into bound type of. So if we analyze the patch properly, we see that there's two main diff lines, and if we see them even more properly, we see that the actual change is just two function calls in the highlighted lines, which is this. And now if we want to show this as a semantic patch, we are going to have to generalize this even further. So this, for example, just shows the first difference in the patch, but we want to generalize it for all diffs in the repository. So for that, we notice that type of is being called from a variable, and it also passes another set of arguments to it. So we define two meta variables, tcx and arg, which can match any other variables with the with itself. So for example, here tcx can match any variable, or in this case an expression, and arg can also match any other expression inside it. So this just says that it removes everything of the type expression dot type of expression, and then it records what tcx is and then replaces it with tcx dot bound type of arg subs identity. And in our example, this patch updates over 200 call sites, which is about 60 to 70% of all the actual things in the diff. But yeah. So the latest developments in Coccinelle for C, in Coccinelle for Rust, are is the CTL engine, which is the same engine that Coccinelle for C has. What the advantage this has over the previous ad hoc kind of matching is that it gives a mathematical and clear way of proposing what changes we want in the files that we want to transform. But the problem with that is that Coccinelle for C, which is made for C, the control flow is quite simple comparatively to Rust. Yeah, comparatively is the keyword. So for example, this is a simple C program, and as you can see the corresponding CFG. So here, if you notice, the F call here is just one single line in the CFG, which makes sense for C code, that there will always be like a straight line of computation when calling fcall. But the moment we switch to Rust, things get messy. That is, we can have if expressions inside function calls, which since if expressions are an expression, since most things in Rust are an expression, and this, though it causes problems there, it will help us later, which I'll show. So we had to find a way to actually incorporate the Rust AST, to convert this into a proper control flow graph. So, yeah, and Rust can get really weird. So, for example, this is a completely normal piece of Rust code which compiles. Yeah, that's weird. So we have to account for all this sort of, I don't want to say nonsense, but yeah. So the so so the job we want to do is represent the Rust CFG from the, not represent to represent the Rust CFG from the Rust AST, which is, without remaking the compiler again, mainly because the Rust language is very new, comparatively. Please don't kill me. And so the language changes very frequently. So if we make a handwritten parser, we may have to. Is it okay? Yeah, so it changes continuously. So we don't want to continuously build Coccinelle for Rust and a parser with it for Rust, which was actually what was done for Coccinelle for C. But C is an old established language. So yeah, so for example, how do we convert this AST into a control flow graph? So the algorithm for that is actually pretty simple. We just recursively iterate through each of the children of the nodes, and just like for non-branching nodes, we just sew them after one another. So this AST, so the control flow goes like this through this AST. And this is a CFG for this specific statement, and for a normal statement like f call 10 without any branching instructions, the CFG is just straight. So not a problem. But the problem arises when we want to do things like this. When there is a branching statement inside fcall. And again, this is just an if, but you can also put while expressions inside function calls, which again makes no sense, but because while always returns units, irrespective of how we break out of it. So it should, it doesn't really matter in that case, but we have to account for it because it's a part of the AST. So this is an example AST of the given if condition, and we want to form a CFG out of this. So to do that, we modify our algorithm slightly, which is here. While iterating through the children, we check if the current expression is an if expression, and if it is, we use the fixed Rust AST if expression anatomy to branch it. So for example, it always branches at the condition, and there's a true branch and an else branch, and after it branches, it goes to two branches and merges at the end. Since if is an expression, it always has to return something, so the control flow at the end merges into one, as it's shown by the second blue circle towards the end, and it branches at the first blue circle. So when we combine this together, we get what we want. For sequential nodes, we get a straight line, and for branching nodes, we can just branch it like this. We just put different conditions for the things we want to check, if it's an if expression or while expression, something like that. So yeah, and we can do the same thing for loops and jump statements, really like any other control flow that we want to do, if we have the AST, which we do since we are parsing it. But there are a few problems with this approach. One of the problems is, since Rust is a function, I don't know if I can say Rust is a functional language. Since many things in Rust are functional, the AST gets really long and really complicated. So for example, this simple piece of code has this control flow. Yeah, not pretty, but, and as you can see, there's multiple lines from the same node. I'll just come to that in a moment. But yeah, one of the challenges is to, like, this is just for a small piece of code. So for huge files, the AST becomes really complex to store and navigate through. So one of the ways to mitigate that is compressing the ASTs. So in Rust, these thin branches we find for different nodes, and we can just losslessly compress them into one single node, and like this thing becomes path expert path segment name ref ident can all be compressed into one node, and anything that comes after this, if it's branch, you can just branch them as children of this compressed node. So yeah, and the second problem we find is how to represent meta variables. That is, yeah, so let's say we have this piece of code. The control flow of this code will be this, would ideally be this, but we add some extra edges to it. Yeah, we call, why I'll just come to it in a moment. The blue edges are what we call sibling edges, because they do not go to the children of the AST, so do not go to the next AST per se, but go to the next children of the parent of that node, which is a fancy way of saying siblings. So, and if it doesn't have siblings, it just goes to the next cousin node. So for example, here the sibling of F would be H, the sibling of G would be this comma right here, as we can see. Why this helps us is if we have to match a patch like this, if we match F, we match, like since we match by control flow graphs, we match F and the open bracket, that's fine. But when we match X matches with G20, but the next node it tries to match, according to the semantic patch, it's a comma, but according to this graph, it says it's G20. But that doesn't match because we want to match a comma. But since X is a meta variable, we take the special node here and match the comma. So the key takeaway here is meta variables need a more complex CFG to navigate through. It is possible to backtrack and check through the red nodes, but that makes no sense. Yeah, so the other point is when I talked about CTL formulas, the mathematical formulas which which represent the semantic patch, they can get really complex really fast. So for example, this earth-shatteringly complex piece of code, which looks like, I don't know, it makes some huge computation or something, is just this. Yeah, not really very complex, but it is when we want to debug it, since thankfully the Coccinelle user doesn't have to go through debugging this huge piece of code, but we have to so that is kind of a challenge when there's one term missing in all those. So we need to find a better way to show the CTL. So some of the other developments are ellipses. The ellipses match an arbitrary number of nodes between two given nodes. Why which it has to be like given that the two nodes are reachable by a path in the control flow graph. But why do we need this? So let's take this piece of code, for example. We make a buffer. We had a buffer previously, and we had to flush it each time we write something to it. But let's say in the new version of the code, we have a buffer which flushes after every character. So in that case, we would want to remove all the flush statements, because that would be just extra statements. So, or it may even break in some cases, I guess. So for that, we would use a patch like this. So for the first two statements, we remove buffer make and replace it with make auto flush. Again, this removes all statements of this form, since this has meta variable I and expression options, so it doesn't matter what is in here. And then we use ellipses, which takes an arbitrary number of path, and which takes an arbitrary path to the node I dot flush, which is the same variable as here, and removes the whole line. That is, it would remove all versions of a dot flush that come after buffer make auto flush, given that there is a path to reach it. That is ellipses, and the final new feature that we'll discuss here is disjunctions. This is not new per se, but I will come to it. It is a conditional matching construct, which means that it can match a bunch of statements, either or a bunch of different statements you want. What I mean by that is, for example, if we have these two pieces of code, we have the same thing as before. We have a buffer, but this time we want to flush it after each new line. So all the statements with a.write_ln with which write a new line will get flushed automatically, but the ones which do not have an ln may not get flushed. So we have to flush them each time we write something. Please feel free to interrupt me if there's any questions. So this is the semantic patch for Coccinelle for Rust to modify these two statements. So the first two lines state that we change all buffer make instances to buffer make nl flush, that's new line flush, if we find any right, and after that we go through ellipses, and if we find any i.write x, that is if we find any write without an ln, we add a flush. If we find a write ln with an I flush after it, we delete that because ln flushes it automatically. And if we have just i.write_ln without i.flush after it, it's just okay. We don't change anything, we only change this stuff in case of the last branch. So there's three possible patches here, three possible paths, and it matches any one of these. So the thing about disjunctions is that it, like in this example, it applies this patch on all the on all the possible paths that match, but it is possible to, I mean, not yet in Coccinelle for Rust, but in Coccinelle for C, it is possible to just take the first occurrence or something, or maybe the last occurrence, whatever we want. Yeah. So, but this was like old news. It's like 1 year ago. So the new things that we developed is that previously disjunctions could only be how much time do I disjunctions could only be expressions or groups of expressions, which severely limited the number and types of disjunctions we could take. So for example, we couldn't have disjunctions of types. So yeah, this is what we could do previously. We could only put expressions or groups of expressions in disjunctions, but now we can put, for the most part, tokens if they make sense in the whole disjunction, like if they make sense branch-wise. So this would mean T1, T2, T3, T7, and this branch would make T1, T2, 4, 5, 6, and 7. But yeah, this asterisk is important here. So previously, since we used Rust Analyzer to parse the Coccinelle, the .coxi file, because again, as I said, we do not want to remake the parser again. To parse the Coxi file, we had to do some weird stuff, like to parse the disjunctions, we had to put in if statements instead of the disjunctions to make it parse to be able to read the thing and put it into Coccinelle. But that wouldn't work in cases like these, because you can't exactly put let x if something, then type 1, if something else, then type 2. Does not make sense. Similarly for function arguments, especially with the ones with different numbers. So yeah, this syntax makes no sense. So we had to find a way to actually incorporate this. And I know that I generally scream profanities at macros all the time, but macros help us here because just like everything, macros are an expression too. And as I said before, expressions can be put almost anywhere in Rust. And as an added bonus, macros can also represent types. So one of our problems is solved that way. Yeah. So for example, this thing turns into a macro here, and since the macros can have anything inside them, we also get access to nested disjunctions. which is helpful. Again, the only problem is parsing them again. The only problem is forming the semantic patch out of the weirdly parsed macros, but at least it makes it possible to parse the stuff. So what we do is we take a disjunction like this, and we turn it into a huge macro, and then get all the possible paths from the macro branches and parse them separately, and then use an algorithm to merge them all back into one big parse tree, and then turn it into a and then use Coccinelle for Rust on that. So, yeah, but we still can't do some things. For example, disjunctions can't be put in place of attributes. So, yeah, we can't do things like this, or we cannot put it in enum variants. And again, this is not really hugely necessary right now, but we are considering other alternatives to this. Yeah, and just as a side note, disjunctions are still a work in progress. So some things are breaking, but it should hopefully be fixed soon. But disjunctions is the only thing that's causing problems. All the other things work fine. So some of the challenges that remain are, as I said, macros. They're a pain in the AST. I've been waiting to make that joke for some time. And the main problem with that is because macros aren't formatted properly by Rust.fmt. I don't know if any other stable tool does it, but we have not found any tool that could do that properly. So we are kind of confused what we should do, and any suggestions are welcome as to how we should format macros there. We did find a bunch of rules to format all macros like a general way, but it was not very good for some macros. So yeah, we are not sure about that. And parallelization is another problem because the Rust Analyzer library we uses the Rowan syntax crate, and the syntax nodes it provides are not thread safe, which means they do not implement the send and copy trait, which makes it really hard to parallelize since, again, we are using the Rust Analyzer crate, so we'd have to modify that. And now I come to the possibly an interesting part of the presentation. One of the possible applications of Coccinelle for Rust would be to address the problem of evolving Rust code with the changing C code. The Rust code in the kernel depends on the C code, so any changes in the C code must represent or must reflect the changes in the Rust code, in the Rust bindings and the abstractions, such that they keep up with the newer constraints. And maybe we can say that it's hard to know who would make the changes in the Rust file once some major breaking changes are made from the C side. So Coccinelle could potentially help with solving this issue, and it would reduce the burden on both the C and the Rust developers. So what we propose is, this would be the ideal workflow here. The C programmer makes some major breaking changes, and that creates a bunch of diffs, and then a specific tool or a human analyzes all the diff files and creates semantic patches out of that, which are then again used to transform the Rust code with Coccinelle for Rust. But the problem with that is that, again, while there's an ideal scenario, a tool which successfully infers the semantic patches just from the diffs would be very complex and formidable, if at all possible, to make. So instead, we settle in a midway position. Whenever the C programmer makes some changes, that creates a bunch of diffs, but the C programmer would also provide a small file called the diff description. I'll just come to what that will contain in a bit. And then that diff description file, along with the diffs created, are analyzed by a tool or a human to create semantic patches. And those semantic patches are used by Coccinelle for Rust to change the Rust files. So that would help with not going through manually and changing the Rust files each time a breaking change is made in the C side. So what I mean by the diff description is our newer constraint set by the C code. So for example, if some FFI types are changed where the constraints of a particular pointer is changed, for example, let's say we want the pointer, we want to tell Rust that for the pointer to never be null, or maybe we can only dereference it a couple number of times so as not to break any borrow checker rules. So we have to find a way to encode that in a diff description file, and then we input that to for the first few patches it would definitely be a human who would check those diff descriptions and the diff files, and then they would create a bunch of semantic patch files for Coccinelle for Rust, which would then be fed into Coccinelle for Rust, and it would change all the files in the Rust side. But a problem with that is that we are not Rust for Linux developers, so we do not have a lot of idea on what are like the major types of constraints that are required to enforce type safety in the Rust bindings and abstractions. So we would kindly request the people in the audience who have experience with making Rust bindings and abstractions to maybe provide us with some examples or changes that occur more frequently in the C to Rust code, so that we can assess the feasibility of such a tool to evolve Rust code along C code in an automated fashion. And at the end, thank you Collabora for supporting the development of Coccinelle for Rust. You can find the links of the tool in the page mentioned here, and please feel free to reach out to the contacts at the end if you have any questions or questions or suggestions. Yeah, thank you.
Just as we can use Coccinelle for also checking for grammar for correctness on Linux, can you use Coccinelle for Rust for similar things in the Rust code as well too?
What do you mean by grammar?
So we have rules to check for APIs. Is there a directory that allows us to also write Coccinelle patches to check for consistency for agreed upon rules that we establish?
Yeah, like if there's specific things you want to check that I don't know, maybe there's some function calls you want to be there to maintain consistency after other things, something like that. Yeah, that's what it was made for. So, yeah.
But do we have that in the kernel right now for Rust?
Right now being used?
For most stuff, we don't need to, because we can encode all of that stuff in the type system. So when in C, you would have to we have to call this before this. In Rust, we can just make it not compile if you don't.
Couple quick questions. Sorry, go ahead.
Go ahead. Okay. So I see that you are using the same as Coccinelle for C expression identifier and so on. How do they compare to the things that you have in the macros, like ID or TY, and whether it's possible to, in the future, maybe to use the same things that you have in macros also in Coccinelle patches?
I'm sorry, I didn't understand the question.
You have identifier, and in the macro you would have ID, or you have expression in macro, you have EXPR. But in Rust macros you have also the types, so TY, path, and so on. I was wondering if it's possible to add more things from macros to the Coccinelle matching.
Yeah, we could.
By the way, there is seats around here if people want to join here. So quick, two things, comment. One is, do you expect to have this in, have you talked to the Rust project or to Rust app or whatever is for distribution so that people can start maybe using it easily or?
No, we have not started any discussions on that yet. Okay. But if anybody wants to test it right now, they could just compile it from here. But again, it would be better if there's a way to easily get it. So.
Another thing you said, human or tool. I guess you tried already to use an AI or something to generate the semantic patch from the.
No, not yet, because we don't have a lot of good examples for the changes that the C changes that actually break the Rust code, and so we don't have a lot of good examples for that. So as soon as we get our hands on some of those examples, we could try to start making a tool, which would. I mean, Coccinelle for Rust already automates some tasks. If you also want to automate the automation, sure.
Yeah, that's what it was.
Yeah.
Okay. Thank you, Tathagata.
Thank you.